what is the shortest possible moment of time? No, I'm not talking about millisecond or nanosecond. What if the universe itself has a fundamental, indivisible tick, an interval so ridiculously small that if you wanted to write it down, you would have to type a decimal point, then 43 zeros, and then 539. At this impossibly tiny fraction of second, our entire understanding of reality starts to fall apart. Space and time might dissolve into chaotic bubbling sea of possibilities. This is the story of Planck time, the ultimate wall our theories have slammed into. It's the story of the moment our physics just breaks. To really wrap our heads around the mind-bending smallness of Planck time, we have to go on a journey straight down from the world we know to a place so alien it breaks our intuition. We have to zoom in, way past everything we thought was small, and then just keep on going. Our journey starts with something we all know: 1 second. In 1 second, your heart beat once. A car on highway moves about 90 feet. For physicists, a second is a pretty comfortable, almost lazy amount of time. But we are just getting started here. Let's chop that 1 second into 1,000 pieces. Now we are at a millisecond, 1,000th of a second. A world here is still pretty recognizable, just a whole lot faster. A camera flash lasts about a millisecond. A hummingbird can flap its wings every few milliseconds. It's quick, but our technology can keep up. It feels fast to us, but on the cosmic scale, it's an eternity. Now let's divide by 1,000 again. 1 millionth of a second. At this point, our human senses are completely left in the dust. To give you some perspective, a single microsecond is to 1 second what a second is to about 11.5 days. You can't feel it, but this is the time scale where high-speed electronics live, the silent, lightning-fast world that powers our digital lives. But the universe is just getting warmed up. Let's go smaller. Divide by 1,000 one more time. Welcome to a nanosecond, a billionth of a second. This is where the example starts to get a little weird. In just 1 nanosecond, light, the fastest thing in the universe, travels about 1 foot. In modern computer, a single core operation can happen in a fraction of a nanosecond. We are now in a realm where the ultimate speed, the speed of light, becomes real, practical problem for designing things like CPU. It's hard to even imagine anything shorter than that. But we have to keep going. Divide by 1,000 again. We have reached the femtosecond. Now that's 1/4,000th of a second. At this scale, we leave the world of electronics behind and step into the world of chemistry. Chemical reactions, the very thing that makes life possible, happen at femtosecond timescales. The bonds holding molecules together vibrate and snap in just few hundred femtoseconds. The only way we can see things happening is with incredibly powerful lasers that shoot out pulses of light lasting just few femtoseconds, acting like a strobe of light for the dance of molecules. Surely, this has to be the end of line. What could possibly be smaller? Well, let's divide by 1,000 one last time in this part of the trip. We are now at the attosecond, 1/4,000th of a second. Now this number is so fantastically small, it's hard to even process. An attosecond is to a second what a second is to about 31.7 billion years. That's more than double the age of entire universe. At this scale, we're not watching the whole atom anymore. We are watching the electrons themselves. The time it takes for an electron to do its thing inside the atom is measured in attoseconds. We are now watching the frantic, blurry quantum dance that underpins all of the existence. We have zoomed in a billion times from where we started. We have gone from a heartbeat to a computer chip to molecule vibrating to an electron zipping around. It feels like we have hit the rock bottom. But we haven't. We have to go even further. We have to keep dividing, not by 1,000, not by million, but by a number so huge it's even hard to name. Something like million, trillion. Down, and down we go, past the limit of our tools, past the thing we can actually measure, down into a place where physics, our very concept of space and time starts to unravel down until we hit a wall, a fundamental barrier. We have arrived at the Planck time. So the Planck time is about 5.39 times to 10 to the power of negative 44 seconds. That's the number we talked about at the start, a decimal point, 43 zeros, and then 539. It's a number so outrageously close to zero, it's hard to see why it isn't zero. But that tiny difference is one of the biggest mysteries of physics. Trying to put this into perspective is almost impossible, but let's give it a try. There are more units of Planck time in a single atom than there are seconds in the entire 13.8 billion year history of our universe, and even way more. Now, this isn't just some random tiny number. The idea is that it might be the fundamental limit. Some theories suggest that it's the shortest possible unit of time that can even exist, the single indivisible tick of the cosmic clock. In this version of reality, the very concept of time below this scale might be meaningless. You couldn't have something happen in half a Planck time. Just like you can take a half step if you're walking on a path made of single brick. It would be the fundamental pixel of time itself. But why? Why can't we go smaller? The answer seems to lie at the massive collision between our two greatest theories of physics. General relativity, Einstein's theory of the very big, and the quantum mechanics, our theory of the very small. Now, there's a great thought experiment that shows the problem. Imagine you want to measure an incredibly short sliver of time. To do that, you need a very precise clock. In physics, to measure something really small, you need a ton of energy. To look at the time down to a Planck scale, you would have to cram an immense amount of energy into an impossibly tiny point in space. According to quantum mechanics, that's totally fine. But according to Einstein's general relativity, that's a recipe for disaster. General relativity tells us that if you concentrate enough energy or mass in one spot, you will wrap up the fabric of space-time so much that you would create massive gravity. It's like trying to measure how thick a soap bubble is by trying to hit it with a bowling ball. If you actually built a device precise enough to measure an interval shorter than Planck time, you would have to pack so much energy into it that its own gravity would cause it to instantly collapse into a microscopic black hole. Now here's the cosmic trap. The clock, the very thing you built to see that tiny moment, would be swallowed by its own event horizon. How would measuring anything smaller than Planck time create a black hole? Let me show you how. I've got this camera and the shutter speed as of now is 1/30. You'll see that as I increase the shutter speed, right, it gets darker and darker. That means that in order to take the picture of it, I need to illuminate this object with something else, another source of light probably. That means that I will require to put some energy into it. But how much energy exactly? Energy required will be equals to h bar divided by 2 multiplied by Planck's time. Now we know what is Planck's time, which is 5.39 into 10 raised to minus 44 seconds. That would mean energy will be 10 raised to 9 joules. Now that is 1 billion joules in a very small space. Now, if you look at Einstein's equation, which is E equals to mc squared, means mass will be energy divided by c squared, and plug this to Schwarzschild's radius equation. You'll get a black hole as big as 10 raised to minus 35. Means if you're trying to measure time lesser than that, you'll get a black hole and it'll swallow everything within this range. Any attempt to see what happens in the span shorter than that, than the Planck time, seems doomed to fall, because the very act of looking would create a black hole that eats the entire experiment. Now this is the wall, a fundamental wall. It doesn't seem to be a technical problem that we cannot solve. It seems to be the fundamental rule built into the fabric of reality itself. At this scale, the smooth, continuous sheet of space-time that Einstein described is believed by some to break down completely. If you think of space-time as a calm, glassy lake, then at Planck scale, it becomes a chaotic boiling frenzy, a concept called as quantum foam. Imagine that if you could zoom in all the way to Planck scale, you would see tiny particles and microscopic black holes constantly popping in and out of existence, churning up space and time like boiling water. In this world, before and after might not even mean anything. The steady flow of time would just dissolve. This isn't just where our clock breaks, it's where our whole idea of time might not even apply anymore. So, where did this bizarre, reality breaking number even come from? It wasn't just made up. Planck time and other Planck units came from the mind of Max Planck, one of the founders of quantum theory, all the way back at the turn of 20th century. And here's the kicker. He wasn't even trying to find the smallest moment of time. He was looking for something he thought was more important, the set of natural unit. You see, physics is built on fundamental constants, these numbers that seems to be same everywhere in the universe, the basic setting of our reality. Planck realized by combining these three most important constants in a very specific way, he could come up with units for things like length, mass, and time that weren't based on random human things, like how long a king's foot was, but on the universe itself. These three ingredients are like the holy trinity of physics. First, you have got c, the speed of light in vacuum. This is the ultimate speed limit in the cosmos, the constant that links space and time together. It's the star of Einstein's relativity and the cosmic law that says how fast anything can travel. Second, there is g, the gravitational constant. This number sets how strong gravity is, the force that shapes the entire galaxies and keeps our feet on the ground. G is the universe's grand architect, the main player in general relativity. Third, you have h bar, the reduced Planck constant. This is the fundamental constant of quantum mechanics. It's the number that defines how pixelated the universe is, telling us that the universe comes in little packets or quanta. If G is the architect of the big stuff, h bar is the rule of the weird random world of the very small. Planck discovered there is only one way to mix these three constants, c, g, and h bar, to get a unit of time. The formula is the square root of h bar times g, all divided by c to the fifth power. Think about what that means. It's a recipe written in the language of universe. It takes the law of the very fast, the law of very massive, and the law of very small and mashes them all together. Planck time is the point where these three huge domains, relativity, gravity, and quantum mechanics, all crash into each other. And that's exactly why our physics breaks down here. Our current understanding of the universe is split between these two amazing but totally incompatible theories. General relativity perfectly describes gravity and the huge scales of the universe. Quantum field theory perfectly describes other forces and the subatomic world. It's like having two master rule books for reality, but one for giant and the other one for the ants. And their rule contradicts each other right at the scale where giant and ants are the same size. At Planck scale, you would need both rule books. You need a theory that can handle quantum nature of gravity itself. We don't have that theory yet. Finding it is arguably the biggest challenge in physics today. It's a giant neon sign pointing right at the edge of human knowledge, screaming, beyond this point, you're going to need a new map. The idea of a Planck scale isn't just a puzzle for physicists. It has huge implications for how we understand the most extreme places in the universe, the very beginning of the everything and the dark heart of a black hole. Let's rewind the clock 13.8 billion years to the Big Bang. We can describe universe when it was million years old, 1 year old, even 1 second old. But as we get closer and closer to zero, we hit that wall. We arrive at what's called as Planck era. This is the slice of cosmic history from the very beginning up to 1 Planck time later. Our physics has no clue what happens in that moment. One entire observable universe was crammed into a space smaller than a single atom, at an energy that's impossible to imagine. The four forces we know today were probably all merged into one single superforce. So what was the universe like before 1 Planck time? The honest answer is, we have no idea. The question, what happened before, might not even make any sense. since the time itself, as we know it, may break down at this scale, there might not be even a before. Asking what came before the Big Bang would be like asking what's north of the North Pole. Time may have actually emerged from the timeless, spaceless state that is completely beyond our imagination. Now let's jump from the beginning of the time to a place where the time is set to end, the singularity inside a black hole. According to general relativity, singularity is a point of infinite density and a zero size, another place where our equations just give us nonsense, like a calculator trying to divide by zero and giving us an error message. But a lot of physicists think that a theory of quantum gravity will save us from this idea of infinity. One popular idea is that singularity isn't infinitely tiny point at all, but a region that is about Planck scale, a super dense nugget of stuff that's governed by the unknown laws of quantum gravity. Instead of being an end of the road for reality, is just another spot where our current map runs out. This all leads to one of the most brain-melting questions of all. If there's a fundamental Planck scale, does that mean that time itself isn't a smooth flowing river, but more like a series of individual discrete frames? Is reality basically a movie playing out one Planck scale moment at a time? This is the key idea in some theories of quantum gravity, like loop quantum gravity. This theory suggests that the fabric of space isn't continuous, but actually woven from a network of tiny, indivisible loops. In this picture, space itself is made of atoms of space. And time isn't some master clock ticking in the background. Instead, what we call time is just another measurement of how quantum bits of space change in relation with each other. If that's true, then our perception of time as just smooth, unbroken flow is just an illusion, an effect that emerges from the fundamentally choppy and pixelated reality. It's like how smooth surface of water emerges from the chaotic jostling of countless individual H2O molecules. The smooth flow of time might emerge from the frantic evolution of quantum reality. We started with a simple question: what is the shortest possible moment of time? And that question has taken us to the absolute limits of what we can understand, to a scale so small it's hard to imagine, and to a wall where our best theories of universe just collapse into paradox. The Planck time is more than just a number. It's a frontier. It represents the boundary between what we know and what we don't, because the universe we can describe and a deeper reality we are only just starting to get a peek at. It teaches us that smooth, predictable world we experience might be one giant, magnificent illusion built on chaotic, quantized, and utterly strange foundation. At this tiny moment, 10 raised to negative 44 seconds, our physics as we know it breaks. But this isn't an ending. It's a beginning. It's a promise. It's a signpost pointing the way toward a new, more complete understanding of the cosmos. A theory of quantum gravity will finally unite the world of the very small and the world of the very large, and maybe finally explain the true nature of space and reality of time itself. The universe, it seems, has built a wall to keep its deepest secrets, and the joy of science is standing right in front of that wall in awe of its sheer scale and dreaming of everything that might be on the other side. If you enjoyed this journey to the edge of reality and want to explore more of the universe's greatest mysteries, make sure to subscribe and join us into the next exploration into the cosmos. Thanks for watching.